Hello, I am Joshua P. Lozada, and this is my activity in addressing. So, for exercise 1, identification of addressing modes. So, for each of the following instructions, identify the addressing modes used. So, for number 1, move AX BX is an example of register addressing mode, since both operands are registers, and the source is a register while the destination is also a register. Then for number 2, move AX parenthesis bracket 1, 2, 3, 4 H. So this is an example of direct addressing mode where its instruction accesses a memory location using its direct 16-bit address. Then for number 3, move AL bracket SI is an example of register indirect addressing mode because stack index register is used and also instead of address, the index or the register is used. So for number 4, move bracket BP plus TI AX. It's an example of base index addressing mode because it uses BP base plus DI index or then add for the memory address. Then for number 5, move CX BX plus AI plus OHH. It's an example of base index displacement addressing mode because it uses BX plus AI plus an 8-bit displacement or the OHH where the operand's offset is computed by adding the base register contents. And for number 6, move DI, which is in a bracket, and AX. It's an example of register indirect addressing mode. The memory address comes from DI, and this mode allows data to be addressed at any memory location to an offset in any of the following registers: BP, BX, DI, and SI. Then, for number 7, move AX bracket BP minus NH. It's an example of base displacement addressing mode because it uses BP with a negative displacement, which is negative 10H. Then for number 8, move AX 5678H is an example of immediate addressing mode, where the operand is a constant value and is part of the instruction itself. So direct. Then for number 9, move AX bracket BX is an example of register indirect addressing mode because this is where the memory address is taken all from BX, and also this mode allows address at any memory location through an offset address. Then for exercise number 2, write code for specific addressing modes. Write 8086 assembly code snippets to demonstrate the following addressing mode. So for number 1, which is immediate addressing, store the value CX55AA into the AX register. So the answer is move AX 55AAH because the value becomes 55AAH because in immediate addressing, the number you in the instruction is exactly the number that gets placed into the register. And in assembly, this number is written in hexadecimal. So we write the letter H at the end to show that it is a hex value. Then for number 2, for register addressing, copy the contents of BX into AX. So the answer is move AX BX because this instruction takes the current value stored in the BX register and makes an extra copy of it inside the AX register. In other words, whatever number BX is holding at that moment is duplicated and placed into AX without changing the value inside the BX. So number 3, direct addressing. So move the value stored at a memory location 1, 2, 3, 4 each into AX. So the answer is move AX, bracket 1234H. So the answer is that because the instruction move AX, bracket 1234H, tells the CPU to go to a specific location in memory. In this case, that address 1234H. Then read the value stored there, and then copy that value into the AX register. The square brackets indicate that 1234 is not the value itself, but the memory address where the value is stored. This way, AX ends up holding the exact data that was at that memory location without changing the content of the memory. So number 4, register direct indirect addressing. So access the memory location pointed to by SI and store its value in AX. So the answer is move AX SI, bracket SI. So because it tells the CPU to use the value currently stored in the SI register as a pointer to memory. This means SI doesn't hold the actual data we want, but it holds the address of the memory location where the data is stored. The CPU goes to that memory address, reads the value there, and then loads that value into AX. This allows the program to access different memory locations dynamically just by changing the value in SI without modifying the instruction itself. So for number 5, which is the index addressing, we retrieve a value from the memory address pointed by the sum of the 10H and store it in AL. So the answer is move AL bracket PI plus 10B because it tells the CPU to calculate the memory address by adding a fixed number 10H to the value currently in the DI register. This calculated address points to the location in the memory where the actual data is stored. The CPU then reads the value from that memory address and stores it in an AL register. So for number 6, base index addressing, access memory using the sum of BX and SI and move the value into AX. So the answer is move AX bracket BX plus SI because it tells the CPU to calculate the memory address by adding together the values in the BX register for the base and the SI register which is the index. This combined value points to a specific location in memory where the actual data is stored. The CPU then reads the value from that memory location and dumps it into the AX register. So for number 3, is that address calculation. Given the base address 1000H, the segment address which is 2000H and a displacement of 0010H. So compute the physical address for the instruction move AX 1000H in direct addressing mode. So my answer is for the physical address is equals to 21,000 each because physical address is equals to the segment times 16 plus the offset. So in 8086 microprocessor, memory is addressed using a segment offset scheme, where the CPU does not use a single 20-bit address directly. Instead, it combines a segment address and an offset to the physical address in memory. So, a segment is the starting point of a 64 kilobyte memory block. Each segment is identified by a 16-bit value. Then the offset is the distance in bytes from the beginning of the segment to the actual memory location you want to access. So by step-by-step calculation, multiply the segment by 16 or 10 each. Then, then we will see the segment is equal to 1000 H. Then here we can see that we can multiply by 10 the 2000 H or the segment. So 2000 H times 10 H equals to 20,000 H. So this gives the starting physical address of the segment and the offsets to the segment start, which is here is 1000 each. So we will only add the offset in that uh, segment. So here we have earlier we have 20,000 each plus 1000 each. So what we get is 21,000 each, or which is the physical address. So the segments tell us the memory block starts at 20,000 each. And the offsets tells us how far inside that block the data is, which is the 1000 each. So by adding them together, we get the exact physical memory location, which is 21,000 each. So the CPU can now access the memory at the physical address 21,000 each. So for number 2, compute the physical address for move AX bracket BX plus SI plus 10H. With BX is equals to 1234H and SI is equals to 4321H. So my answer is, of course, the 25,165H, or which is physical address. So in base index addressing, the CPU calculates the effective address by adding together the base register plus the index register plus the displacement. So base register often holds the starting point of a data block. Then the index register provides an offset within that block, often used for arrays or tables. And displacement, a fixed value added to fine-tune the address. So if combined with a segment address to get the physical address in the memory, physical address equals segment times 16 plus EA. So for the calculation, we're given BX is equals to 1234H, then SI is equals to 4321H. For the displacement, we are given 0010H. And segment, which is in the top, which is 2000H. So for the solution, we will add BX and SI to get the base index. So 134H plus 4221H is equals to 5555H. This gives the intermediate effective address. And the displacement will get the final effective address. So 5555H plus 0010 is equals to 5565H. Now the CPU knows the exact offset within the segment. And the segment base to get the physical address equals to segment base is equals to 2000H times 16. So we'll get 20,000 each. So the 16 is equals to all is equals to 10 each in the here, ito, this one. For then we will now get the physical address, which is the 20,000 each plus 55565 each. So that is my final answer. So for number 4, debug and analyze. Analyze the following code snippet and answer the question. And answer this question. So for given, move AX bracket SI is equals to 1. Register indirect addressing. Then move SI equals to 2000H or immediate addressing. Then add AX equals a bracket SI plus 10H is a base plus displacement addressing. Then move DI AX equals to registered indirect addressing. So I've done the number 1 part, but we can I can explain it further. So number 1, it is a registered indirect addressing because the bracket SI means the memory address is taken from the SI register. Then for number 2, the move SI 2000H is a read addressing because 2000H is a constant value directly loaded into SI. Then for number 3, add AX, bracket SI plus 10H. This is a base displacement addressing because the effective address is calculated as SI plus 10H. Then for number 4, move bracket DI AX. This is a register indirect addressing because the bracket DI with the memory location shall remain by the value in the DI. So we go number 2. If the value at memory location 2000H is 1234H, and at 2000H plus 10H is 5678H, what will be the final value of AX? So we are given here the memory at 2000H equals to 134H, and another memory at 2000H plus 10H is equals to 5678H. So solution is a step by step. So number 1, for AX. So before this instruction, you will see that SI is unknown, so we don't know what is SI. So this instruction will not give a meaningful value yet. So we move in the number 2 step. So move SI to 1000H. So we know that SI now is equals to 1000H. Then for number 3, we now add AX, bracket SI plus 10H. And we only add values at memory 2000H plus 10H is equals to 2010H. So value at 2010H equals to 5678H. So the final value of AX is equals to 1234H plus 5678H, where it equals to 68 ACH. So final value of AX is equals to 68 ACH because at first it takes the value at the memory 2000H is 1234H. Then we add the value at memory 2000H plus 10H, which is 5678H. Then we'll add the 1234 plus 1234H plus 1 plus 5678H in hexadecimal, which gives us 68 ACH. So after this instruction, we get AX is equals to 68 ACH. So for number 5, which is a practical problem, write a small assembly program that loads the value 0x ABCD into the memory location 3000H. Then retrieve this value using the next addressing mode and store it in AX. Then carries the value from AX to BX using register addressing mode. Then stores the value in BX at memory location pointed to by DI using register indirect addressing mode. Assume DIC equals to 4008. So step 0, assume data segment already set up. So what we'll do is move AX 0 A B C D H because X is unacceptable. So we'll do it as H. We'll rewrite it as H. So it loads the immediate value OX ABCD directly into the AX register. Then the next step is this. We'll move bracket 3000H AX, which stores the value from AX into memory location 3000H using direct addressing. Then the third one, move AX bracket 3000H, which retrieves the value from memory location 3000H and loads it back into AX. So it was like swapping. Then the fourth one, we'll move BX AX. So we will copy the value from AX to BX, which is a common register addressing. Then we'll do the move DI 4000H, which sets the DI register to point to memory location 4000H. Then the last step is we'll move DI, bracket DI, BX, which stores the value from BX into the memory location pointed to by DIA using a register in the next addressing mode. So that's all for my activity. Thank you.